Okay, so this is another question that we haven't done before. Um, let's read the question. It says, automobile with radio antenna travels at some speed in a location where Earth's horizontal magnetic field is dead. What is the maximum possible EMF induced in the antenna due to its motion? Oh, okay. So we are dealing with EMF induced motion. So those hopefully remind you of what we've introduced as motional EMF. And I've told you that I will not be using, or at a minimum try to avoid using, the phrase EMF because it's such a confusing term. It's not force. So I think the terminology I've tried to use in the past are something like motion induced voltage. But that I will tell you, it's not a standard term. It's my term. But if you tell it to a competent physicist, they probably know what you're talking about. In any case, in this setup, let's just sketch out some of the things. So we are being told we have horizontal. Let me draw it in perspective view. So it looks this way, but these are horizontal magnetic fields, and we are given its value. And we are looking for the maximum possible EMF, and this motion induced voltage, it's based on this idea. When you look at the magnetic force, that goes as charge times V cross B, and you kind of compare it to the electric force. When you compare that to electric force, which goes as Q times E, there's some visual similarity. You wonder if this V cross B is related to electric field because they're serving the same role. And they are. They pop up in ways that you can detect in an electronic device. So we have introduced that change in voltage is minus E dot change in length. So once you have a quantity that's kind of like electric field, then you can have a quantity that's kind of like voltage. So the motion induced voltage would be the thing we have that looks kind of like an electric field, velocity cross B, dot product with the some length element. So here, so imagine something that's moving horizontally this way, V. Then when you imagine doing horizontal V cross B, also horizontal, then the cross product is going to be vertical. So your motion induced EMF will be oriented in this direction. So for the maximum possible EMF, you want the antenna to be vertical. So you say, okay, I got this vertical antenna set up. Let's see, it's fixed here. It's got some length. It's and let's say that length is given by that L is equal to 1.0 meters. And this antenna is moving at this speed. So that motion induces a voltage difference across the length of the wire. That'll be given this by formula. And we can simplify some things. The way we are drawing this, the velocity and the magnetic field, they are perpendicular to each other, both horizontal, like you can imagine this being X, this being Y direction, they are perpendicular. So for the magnitude of the induced voltage, we can make things simple. V cross B, it'll give you the magnitude V times B. And the delta X, we oriented things so that the direction of V cross B will be along the same direction as the length of the wire, where we can measure voltage across. So it'll be just the length of the wire. So that's it. That should be the motion induced voltage. This is the kind of question, if you're simply looking up the right formula to use, yeah, you can look it up, finish it in 30 seconds, and you're done. I took way longer than I had to because I want you to explain. So my velocity is 119 kilometers per hour. I'm using Wolfram alpha, so I'm letting Wolfram alpha convert the unit. Magnetic field is tiny, 5.6 times 10 to the minus 15 Tesla. Oh, not 15, 5 Tesla. I guess it's not tiny. It's on the smaller side. Earth field can be as high as 10 to the minus 4 Tesla. So, but that's probably actually pretty That's half a Gauss. So that's not small. That's typical. Times and the length 1.0 meter. So that should give me something in the unit of voltage, and we are running answer in millivolts. There's 1.85 millivolt. Yeah, that's pretty small, but it's measurable. Unlike oscilloscope, the oscilloscope we have in class, that we use in lab, they can measure down to millivolt levels. So this is detectable. Like if you had your equipment set up, measuring voltage, drive the car at 119, stop it, you will see the change in voltage.